Okay, I'm traveling this week and will try to have access to internet and to deliver the lectures. But just in case it's not, I'm providing this video for lecture 3 on Tuesday. So um, let's go ahead and dive right in. And I think I'll just share my whole screen. Okay. We left off on Tuesday talking about how to model communication systems and making a point that there's a lot of randomness in communication systems. So, first of all, they're very complex, but yes, we can still model them effectively. But because of all that randomness, not really exactly, right? So, we're going to need to apply what we've learned about random variables and what we will learn about random processes in order to be able to analyze communication systems on average, right? And so we can understand how we can expect them to behave while recognizing that in any given specific instant, something might be a little bit different because there's randomness in it, right? So, and in general, we talked about how there's a trade-off between the model fidelity and the complexity. So, if you want a really accurate, precise model, then you're going to have to build in a lot of complexity. That's going to take not only a lot of engineering time to build the model, but also a lot of time to actually execute the model. And so there's a limit to how far you want to go. So typically, what we'll do is we'll focus on the particular part of the overall problem that we're trying to solve or address, and model that part of the system very accurately with a lot of fidelity, but make a lot of assumptions and simplifications elsewhere in the system. So, and then we noted that while a lot of parts of the system are deterministic, others are random. We talked a little bit about the sources of randomness, and we just mentioned a few of them. One is this phase in the received signal. What is the phase of it? Now, in some cases, the phase isn't terribly important, but in other cases, it's very important. So, depending upon the modulation technique that we're doing. So, if we just move very slightly within a fraction of a wavelength, we will end up with some different phase, right? So because the traveling wave goes through 2 pi radians or 360 degrees as it goes through a wavelength. So if your distance between transmitter and receiver is changes by a fraction of a wavelength, this little delta here, then we will see that manifested as some phase. We might call that phase noise. So we also talked about a very, very important noise source, partially because it's fairly easy to analyze because it follows a Gaussian distribution, but also because ultimately we can deal with a lot of other noises, but this thermal noise or Johnson noise is always going to be with us, assuming we're above 0 degree Kelvin. And we talked about how at finite temperatures, non-zero temperatures, we'll have some motion at the atomic, molecular and atomic level, and that causes some induced currents as the electrons move, and as charges move in a circuit, because there's some finite resistance in a circuit that minute changes in current show up as voltages, and they vary in such a way that sometimes they add, sometimes they subtract. Generally, the deviations are small because there's lots of these different microscopic or molecular or lattice or atomic scale movements of these charged particles, but so they tend to cancel out, and most of the time you have a very small excursion from the mean, but you can potentially have large ones, right? And so most of the time they'll cancel out on average, right? And so we have a zero mean process, but the hotter your system is, or the more noise you have in the system, the broader this distribution will be, meaning that there's a higher probability that you will have large excursions, right? So this curve will be broader, and therefore any given excursion and denominated perhaps in voltages down here, it could be current, it could be amplitude or something like that, right? But then you'll have a higher likelihood if this curve is broadened, that line is going to be higher at any given offset from the mean, and that shows up as more power. So we can see that the variance of the noise process is related or drives the power, the noise power in the system. We talked about, we haven't analyzed it, but we've talked about how the power spectral density, since the frequency spectrum of a random process is uniform, meaning it's a constant value practically to infinity. Okay, not really. If it went off to infinity and you integrated all the energy underneath that constant amplitude in the power spectral density domain, you would end up with infinite noise. So it actually rolls off infinite energy, I meant to say. And so at extraordinarily high frequencies, the noise eventually rolls off in terms of its power spectral density. And so it is bounded in energy. But if we ignore that and look at most of the frequency ranges that we work with in electronics, and particularly in radio communications, its power spectral density is uniform. And it's analogous to white light in the visible spectrum, where it's if we have a relatively constant representation of all the wavelengths in the visible spectrum, then the light will appear white to our sensory system. And so we use that analogy and term this noise process a white Gaussian noise. Gaussian because it has this Gaussian distribution, white because of its power spectral density. And it turns out it's generally additive also. If you have two noise sources and you add them together electronically, then their noise will add also. So we will study this extensively in this course, and we'll often refer to it as AWGN. There's some other things. The input data can be random. The whole initiation rates at a cell tower can be randomized. We don't know how many people will be trying to make a phone call within let's say a 1 minute time frame on a specific tower. It's a little higher up in the communication stack, but it's still than what we'll study in this course, but it's still a random process in communication systems. Electromagnetic waves often reflect off of structures as they propagate from the transmitter antenna to the receive antenna. It might bounce off a building or an interior wall in your house or office when you have like analyzing Wi-Fi, for example. And it might bounce off the ground or the floor or the ceiling. So these reflections at any given point in time are deterministic, but we often treat them as random because we tend to move around, and it's really difficult to model them precisely. And so oftentimes we look at them as a random process. And we, for sure, as we're designing a system, it's rare that we could know for sure all the different reflections that are going to occur in our propagation path. So I think that's where we left off, and then we looked at MATLAB a little bit. We'll look at MATLAB and GitHub in a few minutes also. And let me just tell Google that it's okay. Yes, I want to stay in the call. Okay. So let us assume that we could determine each of these effects for a given system at a specific time and potentially exactly solve the model. What would that tell us about the next instant or state of the system? So even if we could identify, let's say, in that example, all the different reflections, we could solve the system in that particular case, but that's not going to help us in the next instant or some other implementation of the state of the system. So we're going to model these random effects or processes, as we'll discover in the next lecture, using mean, variance, the probability density function, and so on, and calculate the response of the system in probabilistic terms. So now we're going to pivot and hopefully simply refresh some memory on Fourier transforms, and then look at an issue that arises when we model radio communication systems and a solution. So how do we represent a signal? We looked at that on Friday, and we saw that we could represent a signal with an exponential, complex exponential, e to the j omega t plus theta multiplied by a constant that would give you a complex result if you applied Euler's formula to resolve that in terms of cosines and sines. A lot of times we actually use that, the complex representation. But other times, by the time we're transmitting, let's say, we're dealing with real signals, right? And so we take the real part of that and we end up with a cosine. But we have a coefficient out front because that's going to determine the amplitude of our signal. Otherwise, a cosine would give us a peak-to-peak of plus or minus 1 amplitude or volt, let's say, right? And so we might want to scale that to other levels. So we'll have a coefficient out front. And then as the argument of the cosine function, we'll have an omega t or 2 pi f t to represent the frequency, and then plus theta or some phase, right? The arguments, both the phase and the omega times a t, ultimately result in a specific phase at any given time, and that's what the cosine function evaluates and produces a scalar output for a phase. So that's our basic signal in the time domain. Recall that we can use we can use a Fourier expansion to represent signals in terms of a basis function. Typically, that's an exponential basis function if we're using a full Fourier series expansion, where each of the exponential terms will have a different frequency and also a different amplitude. You probably remember, hopefully, that like the classic thing we do when we teach Fourier series expansions to electrical engineers is look at a square wave and how that can be represented by an infinite number of odd harmonics or odd cosine signals, let's say, all with a decreasing amplitude as you go up in frequency. So just trying to spark your memory on this. But then we also talk about Fourier transform, and very, very similar, very, very related, uses those basis functions, complex exponential basis functions. But what we do with the Fourier transform is we take a signal that is dimensioned in time, but really has no resolution in frequency. And then we convert that to the frequency domain, and now it's dimensioned in terms of f, maybe omega, but by convention, it's usually f. And that now gives us a lot of resolution in the frequency domain. So we can look at different slices of frequency and look at what the amplitude of that signal at that frequency. Basically, it's each amplitude at each frequency is contributing to the overall signal. Note that we've lost all our time resolution when we've done that. So the Fourier transform and inverse Fourier transform trade off resolution in the time domain versus resolution in the frequency domain. And when you go to one or the other, you lose all the resolution from the other domain, right? So you know that because when you're looking at the frequency response or spectrum of a signal, there's no t left anymore. So there's no way to figure out, okay, how is this signal evolving over time? We have more advanced tools to handle those type of things, but just trying to spark your memory. So we normally will denote Fourier transforms in the frequency domain with a capital variable and use, as I'm implying, the f or frequency as the variable at which we express the function or evaluate the function, right? So we go from little x of t to big X of f, right? So now, you may not have used this terminology, this Hermitian. It's a fancy name, so why not toss around fancy names, right? So we have the Fourier transform of a real signal x of t has Hermitian symmetry, meaning that we actually have negative frequencies, right? And hard to visualize, hard to understand, but we have for a real signal, we'll have a response at f and also one at negative f, and it turns out they're the complex conjugate of each other. So they're not fully independent. But now if we take the magnitude of these, right? So we square both the real and imaginary term and then take the root, add those up and take the root, then that's the magnitude, right? And we'll see that they're equal, right? So they're the phase is opposite or negative, right? So so this means we only need the positive or conversely the negative frequencies to fully reconstruct the signal. Again, we're assuming it's a real signal at this point, and that's normally what we would transmit, right? It's the real world, so we use real signals. So we don't have to look at both of these. We can only we can choose to only work with one of them, and then always know that we can reconstruct the other part of the signal. Excuse me. Now let's define a term bandwidth. You've probably heard this many times, but let's define it as the smallest range of positive frequencies such that the spectrum or the Fourier transform is equal to 0 when the absolute value of f is outside of this range, right? So that means that there's some bounds to the response, right? And so it's not going to go to infinity. There's some bounds to it, and we look at where that bandwidth or that energy or amplitude goes to 0 in the frequency domain, and that frequency that represents the bandwidth of our signal. Right. So a low pass or possibly a band pass signal has a spectrum located about 0 frequency. Okay, bandpass case, it might be some other frequency, but in a low pass case, this would be 0 frequency, and we see that it has energy around that, but then it goes to 0. Okay, ignore my poor art here. That should go to 0. And this is the phase representation. Also note that it's a negation of what's up here. So the frequency support is the range of frequencies for which x of f is not equal to 0, right? So we're using support here in a mathematical sense. It's where this function is going to be non-zero, and that's going to range from minus w to w, where w is our bandwidth, right? So bandwidth is defined as 1/2 of the support. So we can look at kind of divide these two signals up into two components, and we have x sub plus of f, and we'll have an define that as x of f as long as f is greater than 0, but at 0 at f is less than 0. And conversely, x sub minus is x of s where f is less than 0, right? In this region to the left of the origin, and 0 greater than that. So we've basically taken this signal, the spectrum, and split it in two. Now, right at 0, we scale each of the values by half, so that when they add up, they add up to the proper value. So each of these components gets half of the signal that's exactly at 0. All right, so a bandpass signal's similar, but now we've offset that to some frequency, which is far from 0. Far is completely relative here, but it's no energy at 0. So x plus f is non-zero only in this region here, this f minus half the bandwidth. So and then f, the center frequency, plus half the bandwidth. So now the bandwidth is defined as this region where we have support. Conversely, we have bandwidth down here, and so we could look at the x minus sub minus also similarly and analogously, right? So x f is equal to just the sum of these two components. And recalling now that these are real signals, we can derive this x sub minus in terms of x plus by using the complex conjugate and negating the frequency. All right, so why are we doing all this, right? So one of the things you'll see, I hope, as you do this MATLAB experiment is that if you have, let's say you're modeling a cell phone signal that's in the 2 gigahertz range, 2 billion cycles per second is how fast that signal that is changing. But the data on that, the information content is really only about, you know, it gets complicated, but let's just say it's a megahertz, right? So it's many orders of magnitude less than how fast that carrier is evolving. But if we are focused on the data, but we're having to drag along that 2 gigahertz signal, then we're going to need to oversample it, right? To satisfy Shannon sampling theorem, and to make sure we're sampling above twice the highest frequency in the spectrum. So now we're needing to sample at about 4 giga samples per second and beyond, just to evaluate, you know, a megahertz, or maybe 10 megahertz, 20 megahertz type signal. That's expensive, right? So we need to do a lot of calculations, and but we're just using that carrier, that 2 gigahertz part of the signal, to be able to transmit it using the spectrum that the FCC has allocated to us, right? So we're not using 2 gigahertz of bandwidth. We're using maybe 10 to 20 megahertz bandwidth. That's, you know, I'm just trying to correct myself on that, about the bandwidth of kind of legacy cell phone systems signals. So gets complicated. We'll talk about that in the last couple of weeks of the semester. So that, hopefully you'll see that bandpass signals are inconvenient to work on, to work with, right? So we're going to define the analytic signal corresponding to x of t as x plus t, whose Fourier transform is this x plus of f that we just looked at, right? So this is going to help us derive a low pass equivalent to that high pass signal, right? So band pass signal, right? So this is a band pass signal. Maybe this is 2 gigahertz. Maybe this is plus or minus 10 megahertz or something like that, right? And what we want is something like this, where all the energy is contained here in this low pass area, and we can just set our sampling frequency twice that and be happy, right? So this x plus of f includes only positive frequencies and is complex in this case, right? So we know that because if you just look at this x of f, then it doesn't really satisfy that Hermitian criteria where you have this pair going along with it, right? So if we scratch out this x minus f and only looking at this, then it's not Hermitian, and therefore it can't be real, just real. It has to be complex, right? So that's okay. We know how to handle complex numbers, right? So we can write this in terms of the inverse Fourier transform to give us x plus of t. And we can note that if we use this step function at f in the frequency domain and multiply it by this x of f, it gives us x plus, right? So we can start with this x of f and then multiply it by this step function, and we end up with this x plus, right? So now we can do some inverse Fourier transforms of these things, right? And so we won't derive this. You can trust me, or you can go look it up. But we end up with, as we do this inverse Fourier transform, we end up with this impulse function that, when convolved with x of t, just gives us x of t. Well, along with the scaling factor of 1/2 out front, right? So when this is a convolution operation, right? And so we convolve x of t with an impulse function, then we just get x of t. And we're carrying along that coefficient of 1/2 there. Just make the energy line up, right? So this is a little bit more interesting, right? So this is a J over 2 pi t, and that's convolved with x of t. And this is a very important type of relationship where this x hat of t is equal to this 1 over pi t convolved with x of t. That's called the Hilbert transform of x of t. And might sound fancy. It's actually quite easy to calculate, and sometimes using a Fourier transform, special case of the operation involving the Fourier transform. So, so what this ends up giving us is this low pass signal, right? And so we've gone from this x of f to this x of t, and along with this Hilbert transform signal. So this xl, lowercase l for low pass equivalent, is equal to 2 times x plus f plus this f0, where f0 would been the central frequency of the bandpass, the original bandpass. Okay, so this is a spectrum of the low pass equivalent of that bandpass type signal. Okay, so note that it's not Hermitian; it's complex, right? So it's not not following that rule of a real signal being Hermitian, right? Because it's not symmetrical about the axis, the frequency axis there. So this is nice because now we can choose our sampling frequencies such that it's just twice of this maximum frequency in the low pass equivalent, right? So instead of having to sample it 4 gigasamples per second, maybe we sample it at 40 megasamples per second. So a few orders of magnitude smaller, and that's going to make our calculations our models run much faster. Now, we get even messier here. So I'm going to tell you right off here, I'm not worried about you knowing all this math, right? So the idea, the takeaway that I want you to have is that we can transform a bandpass signal into this low pass equivalent version of it, do our modeling at this much lower sample rate, and then be able to kind of take those results and then re-expand them to the bandpass version, right? So, and that's going to become second nature to you, but all this math that you're going through, you probably won't do again unless you go through a graduate program on communication. So, but we do have this Hilbert transform, and we can take the Fourier transform of that. We get this J sigma x of f here, and so we can go through that and then retrieve. So we get down here and we can see that x of t is equal to the real part of x of the low pass equivalent signal in the time domain, right? So we're in the time domain. So the ultimate, the real x of t, right? So this would be the bandpass version of it, is equal to the real part of the low pass equivalent times this complex exponential at a j to the minus 2 pi f naught t. So this is a carrier frequency, right? So this is a impulse. If we do the Fourier transform of this at f naught and minus f naught, right? And so then we're going to multiply these two together and take the real part of it, right? So to get to here, we go through all these different steps, but I'm going to gloss over that. So so this says that we can do all this calculation with XL, the low pass equivalent signal, and that might be modulation, it might be some amplification, it might be some all sorts of different transforms in a transmitter or receiver, or modeling our channel, that type of thing. And we can do that at the low pass area, and then we can simply multiply at the end, multiply by this carrier, and then take the real part of that and get our actual signal, right? So that's handy. And we can look at the frequency spectrum of this and note that, yes, we're back to a Hermitian type of relationship. And it's a now bandpass centered around this F0, F0 central frequency. We use different terms for it, but it's usually designated as an F sub 0, right? So, all right, the complex baseband signal will work with some, right? So we recall that this X of T is real, but this XL of T is complex. So we can term the real part of this XL of T as the in phase portion of it, and the imaginary part of XLT we're going to call quadrature components, right? So the real and imaginary parts correspond to the in phase and quadrature. So think about when you plot complex numbers on the complex plane, right? We typically put the real axis as the x-axis, and then the imaginary part is 90 degrees, or a quadrature relationship with respect to the real axis, right? So we'll use this terminology. You'll see IQ, the terminology IQ, used a lot in digital communication systems in particular. So it is common to form the baseband signal as a complex signal and then convert to a real signal upon frequency translation to the carrier frequency. And this halves the required, or Nyquist, sampling frequency, right? So again, Shannon Nyquist said that to be able to reconstruct a sampled signal, a digital signal, or it's sampled in time, then we need to have sampled it at least twice the highest frequency in that, right? And I'm saying here that if we look at the signal in terms of an in phase portion, the I, and a quadrature portion, Q, then we're having the required sampling frequency compared to if we sampled just X of T. Now, the explanation of that is, well, really, you don't get anything for free, because if the highest frequency of X of T is, let's say, 20 megahertz, right? So normally we would need to sample that at 40 gigasamples per second. But if we can sample the I portion at 20 megasamples per second, sorry, messing up my mega and gigas. Let's work with megas, right? So if it's a 20 megahertz signal, we would need to sample at 40 megasamples per second. But we could sample the I portion at 20 megasamples per second and the quadrature portion of the signal at 20 megasamples per second, right? So that assumes that we're operating on these with separate circuits, right? And separate calculations. So we're not really getting anything for free. We're now sampling at half the frequency, but we have to do it in two places instead of just one, right? We're having to do it on the I portion of the circuit, that branch, and on the Q, or the quadrature portion of it. So we have to do it twice. Well, as it turns out, it's more than twice as difficult to build a 40 megasample per second analog to digital converter than it is to build two 20 megasample per second ADCs. Now, that frequency range is pretty easy to do these days, but as we get higher and higher in frequency, it gets harder and harder. And that is not a linear approach. So if your silicon engineering is as good as you can do it, and that gives you, let's say, an ability to sample at well, to give you a certain number of bits, let's say 12 bits or 14 or 16 bits or something like that. And let's just say that the best you can do is 1 gigasample per second. So now you can pair those two up, two of those up, try to build them close on the same die, the same area of the chip, so they're very well matched. And now you can sample the in phase and with one part of your circuit, and the quadrature with another part, and be able to handle, reproduce frequencies all the way up to that sample frequency, assuming you have ideal filters, right? So so we use IQ sampling quite a bit just because it helps us implement wider bandwidth, higher frequency signals easier. All right, so that was the end of lecture 2. Let's dive right in. You can pause the video and take a break if you want, but we're going to dive into analog modulation. We're going to breeze through this really quick, and because the course catalog description says we're supposed to cover analog modulations, and they're still used, they're still important, but we're not developing a lot of new systems using analog modulation. We've gotten so good at designing and implementing digital communication systems, and give us a lot of advantages, so that's our preference, right? So you sit down and build a new one, you're going to use that. So we'll first look at modulation in general, and then we'll look at amplitude modulation, and maybe we'll get to doing frequency modulation if we have time. We'll probably run out of time. So what is modulation? It's a coding of an information signal onto a waveform that's suitable for the communication channel that you're provided, right? So such that it can be transmitted some distance and reconstructed at the receiver. This typically, especially in wireless communications, but even in wired systems, involves a translation of frequency, aka also known as spectrum, and the modification of the amplitude, frequency, and or phase of the carrier signal according to the characteristics of the information or modulating signal. Right? So we've got some information signal, we want to move that, but it's not convenient to do it at the frequency that this information is at. So we're going to translate it to another frequency using what we call a carrier signal. And this carrier signal is going to carry the information to the receiver through the communication channel. So, why modulate? Well, most signals are low frequency. It's a relative statement, but low frequency, it means they have large wavelengths, which would require very large antennas, right? Our antenna size is related to the wavelength. Low frequency signals do not travel very far, but probably the big one is that, how would we share the airwaves if everyone is sending everything all at somewhere between 0 and 10 megahertz, right? And so by moving the signal, modulating it to different parts of the spectrum, we can isolate, we can use our filtering technology at the receiver to select only those frequencies that we're interested in, and then demodulate or down convert it to back down to that information frequencies and extract that signal back out. All right, so we're going to look at a little bit of theory, and I'm not going to go too deep into it, but how would we do this frequency mixing and or frequency translation? Now, I'm going to pause right here and ask you to kind of think back to your signals and systems course, and you might have studied a property of the Fourier transform that's sometimes called the modulation property. But if we multiply two signals, then if one signal is a higher frequency and it's a cosine, giving you the impulses in the frequency domain, then we are translating that spectrum to the frequency where that impulse is at, where that cosine is at, right? So that's kind of what we're doing here. We're doing some multiplication, right? So one way of doing that is through a nonlinear device. Now we can a nonlinear device means that its gain, the ratio of the output signal to the input signal, is not a straight line, right? It's going to have higher terms in its Taylor series about this point, or we could maybe simplify it from a Taylor series to just look at a power series, right? So normally the output of a system, let's say an amplifier, would be just some constant gain times the input, right? So we could have Y equals A for the gain times X, the input, X, right? And that would be a linear, right? That's the equation of a straight line, assuming you have zero intersect, right? But let's introduce some higher powers to that, right? So let's say that it's no longer a straight line, but there may be a constant that would be equivalent to our y-intercept and our linear gain. Okay, so and then we can now start to add in some higher orders. So here's an x squared term. You'd have x cubed, x to the fourth, and so on, right? And if you take that out to infinity and you do the right coefficients here, and so then you will see that this series converges to, however nonlinear, I think it has to be continuous. I can't remember, but so we're just going to look at this squared term here, right? So let's say we have two inputs into a circuit, right? Then we'll have a constant out the output. We'll have each of these multiplied by some gain. Here I use C1 and C2. And then we'll also have this kind of squared term here, right? So let's take this x and replace it with x1 and x2 and square it, okay? And here I'm kind of simplifying from this Taylor series to just a power series, right? And now we're going to expand that. So this simply x1 squared plus 2x1 x2 plus x2 squared. Now let's consider that we often are dealing with a cosine signal, or a signal that has could be represented as a sum of cosines, right? Through the Fourier series expansion, right? But let's just keep things simple, and we've got two frequencies here with that our signals can be represented as cosines. Now, if we take that signal and we square it, right? So here we have this x1 squared, x2 squared, and so on, right? So if we square those, then and apply this common trig identity, then we're going to see a signal that has twice the original frequency. So we've taken a signal and we've somehow doubled its frequency. And we've got a constant floating around, some DC signal or whatever, right? And that also happens for omega 2. And we end up with a signal that's at twice the frequency. Then what about this other term? We have this 2x1, x2, right? Don't forget we also have these original terms here, but now we're going to focus on this 2x1, x2 signal. And we'll drop the 2 for now. But we'll say cosine omega 1 t times cosine omega 2 t. And again, using some trigonometric identities, we can rewrite that as cosine omega 1 t minus omega 2 t minus sine omega 1 t times sine omega 2 t. Right? We can also write it conversely, where we sum the cosine angles and then we add these sines right there. All right. So now we can add these two together, and these two terms cancel out. We're adding these two equations together, and we end up with these two terms coming along here. So now we see that our output, that's due to this term right here in this Taylor series expression, because we have a nonlinear device. Right? And now we see that our outputs includes frequencies at the original frequencies, right? We have the original signals. They're scaled down a bit, right? But because the energy is going to some of these other frequencies also, right? So our outputs include frequencies at the original signals, the sum and difference frequencies, and the harmonics of each, right? So we've got these 2 omega 1 and 2 omega 2 and stuff. So we can write that out like this, right? And we've done some simplifications here, right? So we stopped at the second order. We didn't consider that maybe then this signal might mix with that signal and so on, right? So we're only looking at kind of that first order of this nonlinear type operation between these two input signals. So this is important because this is how we can get different frequencies, right? So omega 1 could be our modulating signal, and or our baseband signal, let's say, our baseband signal. And then W2 could be our carrier, right? So we can take a 20 megahertz wide, low pass cell phone signal, 5G signal, and then we can move it to this frequency where W2 might be 2 gigahertz, 2.5 gigahertz, or something like that, right? So very important principle. Again, I think it's kind of fun to work through this trigonometric process. You can do it through this Fourier transform translation property also, and that's probably a lot simpler. But I like the idea of looking at why is this nonlinear thing actually, when we multiply, why does it actually give us a multiplication and these translated frequencies? All right, so now let's dive into amplitude modulation. I think we have about 20 minutes left. Here, recall that when we have a signal, we can choose to encode information onto that signal by either modulating the coefficient out front of it, the amplitude, or the frequency inside the cosine term. We don't always have to use cosines, but we almost always do. A lot of times we do, or some version of it, right? And or we could modify that phase, right? So here we're going to look at modifying the amplitude. So we're going to vary the amplitude of a high frequency carrier wave, that should be wave, not waves, according to the amplitude of the low frequency information signal. So basically, this M of T now is going to be the coefficient out front of this carrier wave, right? And well, that's actually multiplying these two signals together, right? So we're going to do that through, we're going to draw that out here with a carrier cosine omega CT and our modulating signal M of T here, and that's going to produce our output or modulated signal. This figure's from your book here. And so here we have the M of T, here we've got the spectrum of that. Note that it's a low pass spectrum. And then when we modulate it, we have this frequency translation going on, right? And now we're moving that whole signal up to around this central frequency. And the same thing happens in the negative region, right? So it turns out this whole thing is moved up there. And so where our low pass signal has a bandwidth really of B for positive frequencies and B or minus B for negative frequencies, when we translate it, we're going to end up with something that's twice the bandwidth because we're translating that whole part of the signal, right? So now when we look at it, you're going to do this in your second MATLAB assignment. You're going to modulate a carrier, a signal here. So you should end up with a frequency that's moving at the carrier frequency, but its envelope or its amplitude is varying according to the modulating signal, right? The amplitude and the is directly proportional to this signal, modulating signal, and the rate of change is associated with this rate of change here, right? But only if we kind of connect all the peaks of this carrier signal and on the negative peaks also. And that's why we call this the envelope, because it's kind of looking at the maximum excursions of this overall signal, right? And this envelope actually then goes negative here, whereas this negative portion of it goes positive there, right? So you'll actually see there's a phase change right there in the carrier signal. Okay. So yeah, I'm using this term envelope. It's a shape of the modulating signal on the peaks of the carrier, right? So now when we look at this, when we look at this, we're going to well, this is more for the reception. Let me defer on that for a moment. So this creates a double-sided spectrum with a carrier by default, or a DSB double sideband. Actually, in this case, we're not creating a carrier, so there's no energy here at the center. Well, I'm gonna kind of modify that statement here in a minute. So what's happening here is we're creating this double-sided spectrum, right? So there's a upper sideband and there's a lower sideband, right? And this, it turns out it's redundant and wasteful of spectrum and power, right? Because it turns out, right? So this was our original signal, and because it was a real signal, it's Hermitian, and so this part of the signal is almost identical to this, right, via complex conjugate. So this information here in the negative frequency region, which ends up being this lower sideband part, that's redundant, right? So we could choose to just look at the lower sideband or just look at the upper sideband and be able to reconstruct our signal, knowing that it's a Hermitian type of signal. So we will sometimes work with single sideband signals where we kind of construct these things in a little bit more complicated way so that one of the sidebands cancels out. We do some filtering and stuff, but now we're only having to send one of the sidebands, the single sideband. And so we can put all our energy into that instead of having our energy divided between these two redundant signals. We can also kind of suppress this carrier in between, right? And so this double sideband signal is created, and now I'm going to kind of say that we're not going to talk much more about single sideband. Just we don't have the time because we want to focus on digital communications, right? But there's if you read the book, and you don't have to go into that level of detail when you're reading the book. You're going to see that these techniques exist. There's all sorts of different techniques to create these signals and then demodulate the signals and stuff. So we're not going to worry about that. I'm just trying to give you an introduction into these things, right? So double sideband is created by multiplying the modulating signal by the carrier, as we see up here, right? Multiplication is implemented via that nonlinear device, like a diode or some combination of diodes. And that goes back to all that math I just showed you a few minutes ago, right? So more complex combinations of diodes and maybe some transformers, RF transformers, that type of thing, can produce double sideband, suppressed carrier, and single sideband. So we can take two different messages, an M1 and an M2. Now this actually might be an I component and a Q component, or a quadrature component of M. But we can take M1 of T and M2 of T, and now instead of just multiplying by cosine omega CT and just looking at this top branch, then we can shift, do a phase shifter by 90 degrees of this carrier frequency. And well, we know that if you add or subtract pi over 2 in a argument of cosine, you'll get a sine, right? And so now here we're multiplying by a cosine, here we're multiplying by a sine, right? And that's reminiscent of that Euler's formula of a complex exponential where we have cosine plus j sine, right? So here we have this I branch and a Q branch, and we sum those together. And now we have a sum signal, and then when we receive it, we can do kind of the opposite transform here, and then do some filtering, which we'll look at a little bit. So all right, so we're going to revisit this concept here as we look at digital communications, and that's why I'm showing you that here. So how do we receive this, right? So we can receive by multiplying by a carrier and then low pass filtering, right? So we see that down here. This has been the same figure over and over again. So here, this is a received signal. That's what we transmitted, right? And of course, the channel is going to attenuate that. It's going to do all sorts of other effects to it, but we're going to receive this basic signal, M of T times cosine omega CT. Now we're going to multiply by a cosine omega CT. So the same value here. Now we're going to get this E of T, right? What does that look like? Well, it's M of t cosine omega ct times cosine omega ct, or cosine squared omega ct. So let's we can use a little trig identity again that we saw earlier. This cosine is related to the double angle formula 1 plus this cosine 2 omega ct, and we've got this coefficient out front, and there's a factor of 1/2 along there too. Note that now we've retrieved, or we've isolated our original message, right? But we still have this term along here, but it's at twice the carrier frequency. This is a low pass information signal again. So that's what this low pass filter is. So we low pass filter at, we get rid of this. That's actually pretty easy to do. And so we've retrieved M of t in terms of this E of t. And we can look at the Fourier transform of that. We see that the Fourier transform of this E of t signal here, this guy here is the spectrum around M, the message itself, and then this plus or minus 2 times the carrier frequency, right? So we see that here in this part of the diagram. We have these plus 2fc and minus 2fc, and then we have this baseband or information signal. So we've retrieved this. There's some scale factors involved that's trivial to deal with, just this 1/2 type of thing. So, but we filter that out, and we lose that energy. That's gone. That energy that was done there, but we've retrieved that. Now, note that the receiver needs to derive a carrier at the same frequency and phase used at the transmitter, right? This cosine omega ct. We're receiving this. We've got to figure out exactly what that omega ct is, and if there's any phase associated with it. We're not showing it here, but we need to replicate that so that we're really dealing with the cosine 2 omega ct, right? That these omega ct's are the same, and there's no phase offset between these, so we can really call that cosine squared omega ct, because that's what we relied upon to do this, right? So that turns out that's non-trivial. It's not a trivial thing to do. So we can do it. We can recover the carrier. We can do a carrier recovery type circuit, but it's non-trivial. It makes the receiver more expensive. And in a broadcasting type situation where you have one transmitter, but you may have many receivers, right? Everyone that's listening at a broadcast station has a receiver. So any added expense in that receiver then gets multiplied by the number of receivers. So the overall system cost is kind of rough there, right? So the trade-off is let's put a little bit more expense into our broadcast transmitter, and let's send the carrier along with the sidebands to make things easy on the receiver, right? So instead of having to extract this, we're going to not just send this signal, but we're going to send a copy of just the carrier frequency, the cosine omega ct, along with it, right? So what does that look like? Right, so there it is, right? So now when we modulate it, we're going to have this mt times cosine omega t, but we're also going to have this cosine omega t, the carrier, and we'll have some amplitude associated with that, right? So now we can just factor out the cosine omega ct, and we see that what we're transmitting is this carrier amplitude plus the message signal multiplied by the cosine omega ct. So you can look at the spectrum of that. So now we have the spectrum of the message signal shifted, translated to the carrier frequency, but we also have these little impulses, right, that are associated with this carrier, right? Fourier transform of a cosine is is an impulse type function, right? So now we're going to, of course, these are scaled by this value of A out here also, right? So we're going to define a modulation index mu, and that's the peak amplitude of the modulating signal divided by the amplitude of the carrier, right? And as it turns out, we're not going to go into detail for the sake of time, but this needs to be less than 1. If it goes over 1, it ends up being very distorted, real short. This envelope kind of can get clipped here, but worse, it can do nasty things in this area right there. So, and kind of has to be greater than 0 because these peak values are greater than 0. So it's going to range from 0 to 1, and you know, physically, yes, you could overmodulate and transmit a stronger MP to create this greater than 1, but that's going to create severe distortion. So we don't do that. All right, now how do we demodulate this? We're going to I've got to really hurry up here. So we're going to use a diode and an RC network here, and we're going to set the time constant of this RC network such that as that signal goes through this diode, it's going to only pull off the positive peaks of this, but when it gets charged up to this peak value, this capacitor, it's only going to drain off at a rate that's controlled by the RC time constant, right? And then when the next peak comes along, it fills that capacitor back up at charge, and we get a higher voltage and such. So if we set that time constant right, and then maybe do a little bit more filtering. This is doing a filtering operation. Then we see that we're tracing out the envelope using the output of that. So I will. I'll say this also, in that one of the issues with amplitude modulation is because the signal is carried on the amplitude of the carrier. Any additional additive noise, let's say it's static or hum or lightning, all sorts of different things, gets right into the signal and really hard to separate out. So AM modulation is very susceptible to this additive noise. And also note that the sidebands here are directly related to the frequency of the modulating signal. So we'll compare that to angle modulation or FM modulation, which we'll talk about on Friday. All right. Thank you very much. And if you're watching this, it means that I was unable to do this live, so I apologize for that. Hope you get a lot out of this, and we'll hopefully talk to you on Friday. Let's see, stop the recording.